It's a great pleasure to give this talk, and thank you very much for inviting me to give this talk today. So, as was said, so I will be talking about big data modeling for extreme sea surface temperature hotspots in the Red Sea. And this is joint work with my postdoc at KAUST, the King Abdullah University of Science and Technology, whose name is Arnab Hazra. So I will start with a brief motivation. As you might know, the 50% of corals have died in the last 30 years, and this is mainly due to the increasing ocean temperature. It turns out that the coral reefs of the Red Sea have been less studied than those of the Indian Ocean and the Pacific Ocean. So, and KAUST is actually located by the Red Sea, so this was one of the motivations for studying the Red Sea. And so the aim of this work was to model statistically to identify and to predict extreme sea surface temperature regions within the Red Sea, so that what we call hotspots, in future years. So to assess the risk of coral bleaching by the end of the century. And so here in these figures, so the top left one, you can see the Red Sea. So obviously Saudi Arabia is on the east coast of the Red Sea. And each of these red points represent a coral reef. So you can see they are mostly along the coastline, and there are quite a lot of corals, and especially in the south near the Dahlak Island of Eritrea and the Farazan Islands of Saudi Arabia. So in the middle figure, what you can see is a healthy coral, and what you can see on the right is a dead coral. So we need to have some data to be able to do this prediction. And so here what we used was a data product from the project OSTIA, which stands for the Ocean Sea Surface Temperature and Sea Ice Analysis, which is available in that paper. And essentially what we have is daily SST estimates at a very high spatial resolution, so 0.05 degrees by 0.05 degrees, which is essentially a square of size 6 kilometers. And we have the data, daily data available for 31 years from 1985 to 2015, which amounts for 16,000 grid cells over the Red Sea available for about 1,600 weeks. So this is really a huge data set. Especially if you think of a spatial data set, you have to model correlations between 16,000 grid cells. That's really a big task. And so here, to make it a little bit simpler, what we tried to do was to model spatial dependence rather than spatial temporal dependence. And so we themed the data, keeping only 1 day per week and assuming independence in time. So just to give you an idea of how this data set looks like. So first, what we did was to try to understand whether there is a time trend in the data, whether sea surface temperatures are increasing with time. And I will skip you the details, but essentially, there is a time trend. This is something that we expected, of course. But this trend actually varies also across space and across seasons. So we have effects of space, weeks, seasons and years. And it turns out that these effects are not additive. And so we need to build a statistical model that can represent these data features. Another thing to actually look at is the spatial dependent structure. So this represents essentially the relation between sea temperature at a specific location with respect to sea temperature at another location. And of course, we expect that close by locations will be more strongly correlated than distant locations. And so if you just focus on the middle figure here, this is the spatial correlation of sea temperature at all locations with respect to the grid cell that is in the middle of the Red Sea. And what you can see is that this correlation is very strong overall. So we have a very strongly correlated process, as expected, with sea temperatures. But the other thing you can see is, like, if you look at the correlation in the north of the Red Sea, near the Aqaba region, it's about 0.5. But taking another grid cell at the south of the Red Sea, more or less at the same distance from the middle point, the correlation is about 0. So what you can see here is that the correlation structure is also very highly non-stationary. And that's something that complicates the modeling a lot. Now, when we try to model hotspots, we care about extremes, so events that occur in the tail of the distribution. And so here on the right-hand side, what you can see is a coefficient that is called the tail correlation coefficient that describes dependence or correlation in the tail for extreme events. And the message from this plot is essentially we have non-negligible tail correlation for a large portion of the Red Sea, and we need to have a model that accounts for this. So we have essentially a very big data set, very complex, very non-stationary structure, and we want to model everything jointly. So to model this data set, what we did was to try to keep things as simple as we can. And so we decided to model sea surface temperature data in two parts. One part that takes care of the mean behavior, this mu, and the other part that takes care of the residual stochastic variability, this epsilon. So here we index mu and epsilon by t, time, and s, space. And so then we first model the mean. So the mean, we assume that varies with respect to T1, which is the year, and T2, the index of the week within that year, and S, which is space. And then what we want to do is to be able to use the model to predict into the future, right? So we need somehow to include physical knowledge about how temperatures will evolve in the future. Now, how to do this? Well, if you don't have data in the future, the only thing you can do is to rely on some climate model outputs. And so that's what we did. So we assumed that this mean structure will actually depend linearly in terms of a covariate that is actually driven by a climate model. So X2 here, what we did was to actually take it to be the rescaled annual mean sea surface temperature projection for the Red Sea. So we have only one value for the whole Red Sea, but that's something that can be easily predicted for the end of the century. And this is predicted based on a climate model that depends on some assumptions in terms of the greenhouse gas emissions. And so here we take two scenarios into consideration, which are called RCP 4.5, which is essentially business as usual, and RCP 8.5, which is a more pessimistic scenario. So that's how we model the mean. But then you see these regression coefficients here actually depend also on T2 and S. So we depend again on the week and depend on space. And we model them further in terms of splines. So we take 12 splines in time to model the seasonal pattern and 189 splines over space to model the spatial variability. So overall, we have about 2,000 parameters to estimate just for the mean structure. So that's quite a lot, but we also have a big data set. So that's something that can be done. And fortunately, the mean vector can be represented in this form, in this matrix form with Kronecker products, and this makes computations easier. So that's for the mean part. And then in terms of the residual component, one possibility could have been to use a Gaussian process, which is based on a Gaussian, multivariate Gaussian distribution, which is used a lot in statistics. But it turned out to be not flexible enough, right? We have data that are very complex, so the Gaussian distribution was not good enough. Another natural alternative would have been to use a multivariate T distribution, which extends the Gaussian distribution, but this was also not flexible enough. And so what we ended up doing in the end was to use a mixture of K student T distributions. And that's what you see here. So this is what we call a Dirichlet process mixture. And so here you have mixture probabilities, this pi k that needs to be estimated from the data. And these FTs are the multivariate T distributions with their own parameters. And so these depend on some parameters. AK is a degrees of freedom parameter, which controls the overall dependent structure. Tau k is a nugget effect that controls the small scale variability. And phi k is a matrix of weight that needs to be estimated. So essentially, the distribution is parameterized in this way. We have a matrix H, and in this matrix H, we will actually put basis functions. So let me show you what kind of basis functions we choose. We choose what is known as empirical orthogonal functions. These are essentially eigenvectors of the spatial dependence, spatial covariance structure. And they represent certain natural geographic characteristics from the data. So for example, you can see EOF number 2 here represents the gradient between north and south. EOF number 3 represents the contrast between the center of the Red Sea and the ends of the Red Sea. EOF number 5 represents the contrast between the southwest and southeast. Right, so you can see that these EOFs actually have quite nice and interpretable characteristics, so that's why we use them in practice. So then these things will actually be pre-computed before we fit the model and put in this matrix H, and then what is left to do is only to estimate the weights that are corresponding to these basis functions in this phi matrix here. Okay, so overall the model looks like this. I will skip the details, but we can write it hierarchically and use Bayesian inference for that model. We can compute the model properties, the mean, the covariance, the tail correlation, and everything is as expected. We have a very non-stationary structure driven by the covariates, and we can capture extremal dependence as we wanted. So I will just now come to the application and show you some results based on this model. So first of all, we have to choose the RCP scenario, so the greenhouse gas emission scenario that we consider. And so here we took these two cases, 4.5 and 8.5. Again, RCP 4.5 represents business as usual. This is this kind of blue curve. And 8.5 is this RCP that is more pessimistic, with a more kind of linear increase in temperatures. And so here we did the modeling based on both, and I will be presenting mostly results based on RCP 8.5. So first of all, the model that we consider here is called this LTP-DPM, so low-rank T process based on Dirichlet process mixtures. And we have to choose two parameters. One is K, the number of mixture components, and L is the number of basis functions. And so to choose these parameters, what we did was to run a cross-validation study. And it turned out that the best model was our model for K equal 10, so 10 mixture components, and L equal L1, which was about 20 basis functions. And so later we actually choose these values to make the inference. And then once we have this, we can draw inference. So let me just describe now these probabilities that we compute from the model. And so the first probability that we consider here is we fix a certain region of the Red Sea, D0, and we fix a certain temperature threshold U, and we look at the probability, based on the model, the probability that all the values within that region, D0, exceeds the threshold U. Well, not all the values, at least one value exceeds the threshold U. And this other probability on the right-hand side is the probability that all the locations exceed the threshold U within the region. So that's what we call type 1 of this probability. So that's considering an equal bleaching threshold U. And then type 2, what we did is the same thing, but actually replacing this fixed temperature threshold U by something that varies across space. So here, instead, we fix a probability level P, and then we compute the threshold for each location. And this is a bit more in line with coral bleaching theory, which states that usually corals are slightly adapting to their environment. So for example, the bleaching threshold in the north of the Red Sea will be lower than in the south of the Red Sea. And so these are the three regions that we considered. So in yellow here, this is a region that is next to KAUST. In green, this is a region that is close to the Farazan Islands of Saudi Arabia, where you have a lot of coral reefs. And in purple here, this is close to the Dahlak Island of Eritrea, with also a lot of coral reefs. And we computed these exceedance probabilities. That's what we got. So I don't want to describe everything in detail. But the bottom line here is these estimated probabilities are pretty high. And this indicates that there is a high chance of coral bleaching by the end of the century. And then what we do is to estimate hotspots, so the regions themselves that are at risk. And so we did that based on RCP 8.5 for the end of the century, based on different, temperature thresholds, 33 degrees, 33.5, and 34 degrees, and 2 different weeks, week 40, 33, and 40. And so if you just look at the bottom panels, week 40, what you see here is that the estimated hotspots really cover a very large portion of the Red Sea in the south part of the Red Sea. And these areas, these hotspots, in fact, cover the Dahlak Island and the Farazan Islands of Saudi Arabia. And so this indicates that there is a very high chance of coral bleaching in these areas by the end of the century. So I just want to conclude here very quickly, if I have a little bit of time. I'm not sure if I'm already out of time or not, but essentially what we have done is to propose a low-rank semi-parametric Bayesian model for large spatial data where independent replications are available. And the model is very complex. It has a non-stationary mean, covariance structure, extremal dependent structure, and so on. It can be fitted by a Gibbs sampler, which is fast. And the results suggest that very large areas of the Red Sea that include very important coral reefs are likely to experience very extreme sea surface temperatures simultaneously around the end of the 21st century. And this may have very dramatic consequences in terms of coral bleaching and mortality if mitigation measures are not implemented. So in future research, it would be also interesting to generalize this modeling approach in order to capture space and time dependence in order to assess whether these hotspots, in fact, can persist over time, over consecutive days. So this is something we have not done, but we know it's really important for coral bleaching. So that's really something that we want to study next. So with that, I will thank you for your attention. And this work is now published in that paper. So thank you very much.
Raphaël, thank you for that detailed presentation. It was fascinating to learn more about not only the research you're doing, but a lot about the model you're using. And thanks for sharing where people can kind of find out more about this work in that paper. So we have quite a few questions in the Q&A, and I am not confident we are able to get to all of them. So if you want to connect with some of the folks that maybe we didn't get to, feel free to do that in the Q&A section, Raphaël. But we'll start with, how many sampling stations do you have measuring the temperature behavior over time?
So how many locations, right? So here, this is the number. This is 16,703 grid cells covering the whole Red Sea. And so this may not seem that big, but in fact, if you think about it, this is a huge number because we are trying to model spatial dependence. And this means we need to characterize this or to compute or to model this covariance matrix, which would be of dimension 16,000 by 16,000, right? Which is 256 million, right, entries. And we need to do that over, knowing that also this dependence is evolving over time, right? So that's where the big data part comes in. Yeah.
Absolutely. That is a lot of data that you're working with for this analysis. Thanks for giving the number on that one. Can you talk about how you're doing the data collection and how does it take into account the depth in some areas of the Red Sea?
Okay, that's a very good question. So we are not working on the data collection. That's in short. What we did was to actually take this data product that is available freely online. So this ocean sea surface temperature and sea ice analysis. But what they do is to essentially generate daily sea surface temperature estimates based on satellite measurements and combine this with measurements from buoys in order to calibrate that and to get like a very accurate data product. So I am doing the statistical modeling. Other people do the data collection. But fortunately for us, we could download this data set online freely.
Absolutely. So it's a group effort there. And it's awesome to hear about all of the open source data and tools that people are using in the analyses.
Yes.
Let's see. All right, one more question, and then there are still a few left in the Q&A. But could the same statistical model be applied to other types of environmental data?
Yes, absolutely. So here we had this sea surface temperature data set. So we use that model for that. But of course, the statistical model is very generic in itself. And as I mentioned, it's very flexible. It can capture all kinds of non-stationarities in space and time. So yes, I mean, you could apply it to other type of data potentially with some changes, because here we use the Dirichlet process mixture of multivariate student T distribution, so it has support over the whole real line and things like that. But with small changes, yes, we could definitely apply it to many other types of environmental data. Yes.
Okay, that's great. I'm imagining all the sustainability people in the attendees kind of having their brains churning of how they could use this model now. So thank you.
Thank you for the questions. Yes.
Yeah, of course. That is all the time we have today. But if you are interested in learning